So this is just going to be a brief introduction to ThermoFlo. ThermoFlo is our, well, first let me just give you a quick background of our company here. TES has been around since '94, and as I mentioned, Ben Zandy, who will be talking later here, actually founded it along with his partner. And it was put together with the intent of serving mainly automotive and aerospace communities with any kind of thermal management problems, specifically in electronics. And as time has passed, we've added in more features for general purpose CFD, stress and vibration, as well as just general heat transfer solutions. We also have had a lot of focus on any kind of custom solutions or automated tool development, so doing actually software packages specifically for companies. So ThermoFlo is our latest package, and has been developed mainly through funding from the Army, and they were looking for a new way to solve their underhood problems for various tanks that their tank system has, looking specifically into the thermal management systems. So ThermoFlo is a 1D package and allows for the heat transfer analysis and the pressure drop calculation to be conducted. It has a component-based approach, so that you're using the drag and drop approach, where each component could represent a full system, or just a very simplistic pipe, say. And the components are based on empirical correlations or testing data or any kind of other tabular or functional data. So it could be based on something physical, or it could be more of a theoretical model if it hasn't actually been constructed yet. And what this allows you to do is a virtual rapid prototype and testing, where you can quickly interchange any kind of different components in your system. You can tweak model properties. With a single click, you can go through and change a geometric property for your whole model without having to go through and like you in 3D, where you're going to have to modify the mesh or update the boundary conditions. This will all just be handled automatically. Some of the main features are complex custom math expressions, and we'll look at this a little bit later, but really what this allows you to do is, without having to create any code, so without having to write any subroutines, you can model virtually anything through algebraic functions, and then tab tables that can be functions of those algebraic functions, and then functions that can be relative to the tables. And through that, you can duplicate any kind of complex correlations. As I mentioned, it is a drag and drop interface, so you're just pulling components in from one side and then connecting them up, and you'll see that in a video later on. The parts are fully customizable to a point where you can create your own components, or you can take components we've provided and change the names, change the language. If you want to change the defaults, you can do that, or if you just want to add in any kind of new features to adjust it to fit what your needs are. We have different load cases and global variables, and so this allows you to quickly do a what-if analysis on the whole thing, where you could say, I want to look at the high speed, I want to look at the high load, and I want to look at nominal, or if you want to use your hot day, your cold day, you can look at various simulations, and just by pushing one button, quickly run a batch on everything. We do link to external programs within the software. You can create any kind of internal or external function, and if it's an external function, it's actually going to be looking for that value from another program, or it's going to be actually, if it's going out an output, it'll actually be passing that to another program, and then that can be put anywhere within the code. And we do have both a steady state and transient analysis. The thermodynamic analysis, which you're going to go into quite a bit more detail later on, Ben's going to handle this side, allows for solving for the conservation of mass and first and second law of thermodynamics. It's made up of individual components and processes that can be put together in a system, and it solves gas, vapor, and combined power and refrigeration cycles, while automatically evaluating the isentropic efficiencies, second law efficiencies, COP, for refrigeration and heat pump cycles. And at the same time, you can get the pressure loss calculation for friction or minor losses, and it gives you full access to the NIST fluid library, so that you don't have to go through and look up properties. That'll be for all your refrigerants and coolants and some more theoretical refrigerants as well. This can also be tied into the two parts, the thermodynamic part and just the standard thermal fluid network can be tied together through heat exchangers, so that if you have, for instance, your car underhood, you could actually be modeling both the refrigerant system and the main coolant loop and having them coupled in through components. Some additional features are that we have also have an RC network. This is a resistance capacitive thermal network, so that you can represent any solid through a mass, and then actually have this tied through resistive links, and then that can couple directly into your flow bars for your fluid, and any fluid path will have a option to have a solid around them, and then you can tie directly to that solid or directly to the fluid, so that you can create fairly complex thermal systems and see their coupling to the flow. As I mentioned, we do have batch runs, and one thing that you can do is you can add any kind of parametric variable. So you could say that I want the temperature at -50, 0, 50, and 100, or I want it from -50 to 100 with four different steps in between, and then it'll automatically create a run for each of those circumstances. You don't have to go and create a load case for each one of those. And then there's several different modeling support things. One is the smart modeling tools to prevent any kind of modeling errors, where it's going to give warnings and errors if it does see anything that may be a problem, and you can adjust these for your industry so that they're not set for perhaps a 1 meter diameter pipe is reasonable to some people, but is ridiculous to others. So you can change what those are to prevent any kind of unit issues. For model overview, we have a list view or a tree hierarchy where you can quickly see everything in your model. It's a schematic view, but since we have submodels, at times you can't see everything in the submodels just in that one screen. You have to kind of go into the different submodels. That keeps it clean to the end user. And for the overall interface, it's dockable and tab window, so you can move things around, put everything wherever you want, and that you kind of get a feel for as you're using it. So the first type of problem I'm going to discuss are thermal management systems, and the way we're going to break this down is kind of go into the different applications that this can solve for, and then if you have any questions about these specific applications, we can have set up a meeting offline, or in the future we'll have more videos associated to these specific industries. But for thermal management systems, we're talking about anything where you have a heat exchanger with a coolant loop, and you're trying to cool something. In this case, it's an automotive cooling system, but it could be anything else. And then this can be used to find the appropriate sizing for the radiator, for pumps or fans, or setting the thermostat, and then can show you what the overall system efficiency is. So here we see a video, and this is an automatic cooling system, but over on the side we see our different components, and you can categorize them into any different folders. You can also quickly do a search, and it'll find everything that's associated to that, and that'll be searching the name, the path, and you can also add a description for any component. And then as we look up here on the top, you see we have a ribbon interface. So everything that you need should be very easily accessible. Within all of these components, there's potentially a lot more information. So here we're going to look into the inside of a component, and this is made up of several different flow bars. In here we could change the images, change the titles. As I mentioned earlier, everything within ThermoFlo is completely customizable. There's nothing really hard-coded. Here we see the equation for U, and then as you go into our calculator, it'll actually show you a nicer version of that expression, and you can look in and see any kind of solver variables you can add. You can add in user properties which were created for this form, tables and functions, and then use these to create your calculation. This is kind of the heart and soul of the user interface for ThermoFlo. For all components, you're going to have a set of user properties, and that's what the user is actually going to see. And then this is laid out in a form so you can put those into frames and have that as an advanced frame so that they know they don't have to necessarily answer that. And then that'll make a sort of a user property window like this. So the end user, this is generally what you're seeing. Once a component is created, then that's going to go into the database, and you'll just be pulling in from that. We also have fairly simplistic models that are included. Here's just like a straight pipe, and so you can see there's only a few questions asked about that. But what's actually going to get sent to the solver are these solver properties here. So at any point you can look at what the true solver properties are, and that's what it's going to solve on. That'll convert all of the units. One nice thing is that on any property you can always enter in whatever unit you happen to want, so that you're not having to initially say, I want everything to be in English units or something like that. Everything can be changed as you bring the data in. You can enter it in whatever you want. Here we see a table. Anytime you have a table, you can quickly look at a chart of it to make sure that that's accurate. And looking into the detail here, you can see there's another component here, and you can size where your ports are so that they'll be in the right location. You give them all names so that people know how to accurately do them. And then you can also apply any kind of in the basic things. The way it works, you have your solver properties, and then those are actually going to be tied into your user properties. So here we see that like the cross-sectional area is tied in this situation to the diameter. And for our components we've included, that's automatically done. But as you create your own components, that'll be kind of how it's set up. And we have some videos explaining how to work on that. Next, one thing you can do to your model is add in any sensors. And this can be as simple as just saying, I want to see the temperature output at this point, or it could be more complicated, showing a full function so that it could be maybe determining the efficiency of your radiator. And then that, while it's running, we'll plot that. When we go to run, it's going to give us errors and warnings. And here we can see there's an error. If you just click on the error, it immediately takes you to the form where that is. And in this case, it's just that we haven't entered in a property. And then warnings will be saying that something is out of the expected range, generally. Okay, so here we see another sample of a heat exchanger model. This is a more complicated version of a 1D heat exchanger, and this was created from a correlation. These red lines are actually representing thermal length. These would be a solid node. The capacitance is in between here, and then everything else is fluid running through. So we have the coolant path, and then we also have the air path running through. And then these are using correlations, using a Case and London approach for a heat exchanger. And then the actual correlations have come from a paper referenced down below. So that you can then, to use these heat exchangers, you're just going to have to enter in to the end user what's the width, width, depth, and height of it. What are the fin thicknesses? If it's louvered fins, what's the angle of the louver, and things like that are available. Really, for the most part, you can go out and measure with a ruler. So this should be something that anyone in the shop could go out and tell you what the values are going to be. Some other examples for thermal management systems are avionics cooling, data centers, solar panel cooling, and really anywhere else where you're trying to remove heat, as I mentioned, from one location to another. Okay, the next thing is just water distribution systems, and here we have an example of a water heater in your house. So say you want to know what you need to set that water heater for so that you know you can get your 10-minute shower in the morning. what temperature do I need to set that at for the summer, what temperature do I need that for the winter. And then in this case, we looked at it with an electronic control valve so that it's actually trying to just fix that temperature for the shower. So you can just say, I want it to be, the temperature to be 110 degrees, and then it'll adjust the hot and cold valves to ensure that you have that. And so one nice thing about ThermoFlo is it's letting you test your control algorithms out before you actually have a prototype. And here we see the system. Everything starts off with a different temperature. So we have both a winter and summer condition where the initial temperature is going to be different. And it's going to run both of those. You can see how we actually have files that are linked externally to a MATLAB model. And the reason the winter and summer is going to make difference is that we are actually looking into the solid of the pipes. So the copper pipes are starting at a colder temperature in the summer or in the winter than they are in the summer, so that you're losing more heat to that because it is a transient process. And then the water heater, as it gradually goes through, the temperature of the water heater is going to be dropping, and eventually you won't be able to maintain that shower temperature in this condition. Some other examples of water distribution systems would be any kind of city-wide distribution. You can use it for sizing of pumps, looking at what-if analysis, what if something breaks somewhere, oil, natural gas, manufacturing, chemical processing, and commercial buildings. Okay, so I'm going to pass this over now to Ben Zandi, and he's going to get more into the thermodynamic approach of solving systems. And as I said, these can be coupled together, but they are very different in the way they work.
Thanks, Hamish. Yeah, as Hamish said, the thermodynamics approach is really it's a behavioral approach that you have the components each having following certain rules, and they're hooked up together, just as before, just the normal ThermoFlo approach. The first thing I want to show is refrigeration systems. Here we're talking about vapor compression refrigeration cycle. Things that are normally we're looking for is the heat removal from the refrigerator space, power requirement, efficiency, and that sort of stuff. So we look at a simple video next that actually shows how you can put together this example. Let's say we want to solve a two-stage refrigeration system that you have a high-pressure and low-pressure compressors, and we have a condenser, and then you get the valve that gets the pressure down to a flash chamber, and the flash chamber, you get part of it, you get the extract the steam out, and then you get the liquid go down to the evaporator, and then you have a low-pressure compressor. And in this problem, we know the pressure levels, and we're trying to figure out what's the evaporated mass fraction and the usual things. With ThermoFlo, you basically drag and drop things on the screen, regardless of the complexity of your problem, and it will give you all the information you're requesting. So here, first we create a model, we give it a name, two-stage refrigeration, I guess. And with that, it opens up your screen, and we see the main canvas. I just make it a little bit bigger so we can use your components. So we go to the thermodynamic components. We get a high-pressure compressor up there. So we have the high-pressure refrigerant going into a condenser, and then from the condenser, we need a valve. And the valve gets the pressure down to a flash chamber pressure, which is our intermediate pressure. So we put it right there. And then we need another valve to get the pressure down to the evaporator pressure. Now we need the evaporator, and we get the evaporator, and you just put it wherever you want on the screen. And then we need a mixing chamber to get the fraction of the flows coming from both sides before it goes to the high-pressure compressor. So we need a low-pressure compressor down there that's attached to the evaporator. Now you can just put things, make it look nice, and all that good stuff. After that, all you need to do is just get the outlet of one component to the inlet of the next, and that's how you put your system together. You need to keep in mind that when you connect things this way, these are ideal connections. There's no pressure losses in these things. If you wanted to look at the pressure losses, you could put a pipe system there. So now we just connect things together this way, and everything is connected. So just make it look a little bit better. So now the next thing we want to do is to go and set the loop fluid. So we go there and we choose the fluid. By default, we get water. Here we need the refrigerant. So we double-click on it. You have all the NIST materials available to you. Go to the refrigerants, and we want to pick 134A. And we pick that. So that's now our fluid. Now here's a good place to give the mass flow rate, because that's where all the flow merges. So we get the mass flow rate at that point, double-click on it, and we give it 1 so we can do per kilogram analysis. And now let's set the pressure levels. So we go to the inlet of the low-pressure compressor. We set the pressure there at 0.14 megapascal. Just get the pressure thing and enter 0.14. Change the unit to megapascal. The same is said, you could just change your default to what you want, so you don't have to change it every time. So here's our low pressure. And then we go set the highest pressure in the model at the outlet of the high pressure compressor. And I believe that's 0.8 megapascal. We set that right over there. And again, we want to make things look nice. You can just put it out of the way and, you know, and do all this line up the lines. And then we go and set the pressure at the intermediate pressure when it's coming out of the first valve. So we just set the pressure there at 0.32 megapascal. Okay, and we're almost done. Now we need to just set, if this is an ideal system, what comes out of the condenser is going to be a saturated liquid. So at that point, we just go there and set quality equal to 0, which is the default value. So I don't have to do anything with that. Just clean up a little bit. And also at the bottom, we have an evaporator. If it's ideal, it's going to come out as a saturated vapor. So we go there and we set that quality equal to 1. That's about all you need to do. You can solve the problem. No need to look up steam tables, refrigerant tables, and iterations and all that. Now let's look at, if you wanted to see the compressor, you double-click on it. It takes you to the menus. Whatever's not checked will be calculated. So, and then you go on. Let's look at the evaporator, for example. You can look at the things if you wanted to use. Here we chose to give the pressure drop of 0. That's the ideal thing. If you didn't want to, you could just take the effect of all the things in it. So now you run it. Click a button and it's done. And the results come by default. Temperature is shown as all the nodes. I'm going to turn that off. And if you right-click on any component, you can see the abbreviated results of summary results of this component. Okay, so that's the video. So now, if you I'm going to go to the next page. Okay, you go to the detailed result. After you run something with ThermoFlo, it produces these detailed results. So for that problem we ran, here's a table of all the fluid properties with all the nodes. So we can see, pressure, temperature, specific volume, internal energy, enthalpy, entropy, quality, mass flow rate, and volumetric flow rate at all the points. And you also have a detailed result of your components. So we had 2 compressors, calculates even stuff that you didn't ask for. You know the power input, you see the condenser, heat loss, the evaporator, the mixing chamber, and everything. And at the end of it, it recognizes that this is a, whether it's a power-producing device cycle or it requires power. So here it calculates your coefficient of performance. For the refrigerator, it would be 4.47. If this was used as a heat pump, would be 5.47. So that easy, you just basically run a system. Now, some of the applications of this type of thing is in battery chillers that we've actually used ThermoFlo for problem like that. We have commercial refrigerations and heat and air conditioning and things of that nature. Let's quickly look at the next application. Is the important application, gas turbine system. Here we have open cycle usually that utilize rotating machinery like compressors and turbines. They're all based on air standard Brighton cycle and its modified versions. So we have compression through the stages of the compressor. Then we have heat addition that you could have in a combustion chamber, or you can have in the reheater or regenerator. Then we have expansion that's done in the turbine stages, or if you have a jet engine, you have also a nozzle for expansion, and also the heat rejection. So here I'm not going to go into a very fancy example of that. You were just looking at a, for a electric power plant. So you have a compressor and a turbine, and then you have a regenerator that heats up the air before it enters the combustion chamber. You could just as easily have intercoolers in the stages of the compressor. You can have reheating in the turbines by just if you chose to do that, and see what happens to your efficiency. We use, you could use any kind of heat exchanger you want from the ThermoFlo components, or to design your regenerator. Other examples, the types of applications that you could use for gas turbine is jet engine propulsion systems. Shown at the top here, you have the examples: turbojet and turbofan and ramjet, and electric power generation systems with much bigger compressors and turbines. So that's one application that ThermoFlo can be used. Another one is steam power plants. You can use a thermodynamic type of approach to look at the steam power plant. Here you have vapor power cycles, where you have alternatively vaporizing and condensing the steam. It's based on Rankine cycle and its modified forms. And here the pump, you have components such as pumps, boilers, steam turbines, and condensers and feed water heaters. And of course, the components are huge, but thermodynamically they can be modeled, as we've all seen. Here's a sample problem with a regenerator using an open feed water heater. You have a high-pressure turbine, and fraction of the flow comes out, goes into the feed water heater, and the rest of it goes to the low pressure. And the cycle is working on the low pressure of 10 kilopascal, and the intermediate of 1.2 megapascal, and 15 megapascal is the highest pressure. And then we have the condenser pumping the flow up to the intermediate pressure, and then you further pump it up to the high pressure. You go through the boiler and back to the turbine. And here you may want to ask what is the feed water mass fraction? What's the cycle efficiency? Or you could solve the problem from any direction that you want. So here, without going through ThermoFlo, you could just basically drag and drop all the components, and you, just as before, you put it here, and you set the mass flow rate as, again, 1 kilogram per second, because we're just looking at per kilogram analysis. We set the fluid to water, so we didn't have to do anything with that to change it. Set the pressures as before to the values, and that's about it. You run it, and as before, you get the quickly the values of all the properties at different points without using any steam tables or any types of iterations. And you can go to the details of the components. You see the turbine behavior, you see the pump behavior, and the condenser, boiler, and it determines for you that the cycle thermal efficiency for this example was around 48%. So these are some of the problems, but one of the most important applications of ThermoFlo, as you probably imagine, it comes as a very handy tool to have. You could use it to figure out engineering systems and do quick calculations. And it actually relieves the engineer from looking up tables, going into the performance charts, and that sort of stuff that there's usually a lot of error involved with it because, it happens. So as an example, there are many examples you can think of. You could look at the heat exchanger design. You can look at flow distribution pumping. You can look at a single component in a thermodynamics, or just look up fluid properties. Here's a very simple example. Let's say you have a complex water flow system, pipe system, and you go in from a to 20th floor, for example. You have a lower reservoir, and then you have another reservoir at much higher, 100 meters above, and you know everything about the system. The first thing is that you may want to see what kind of a pump horsepower you need. So you run ThermoFlo with the pump horsepower unchecked, and it will solve it for you. And then let's say scenario B, that you know the pump horsepower, and you want to see the mass flow rate. So you enter the pump horsepower, and you uncheck the mass flow rate, and that will solve the mass flow rate for you. You could even see, what kind of a pipe diameter you need to get the water up 4 kilograms per second to the 20th floor. It will solve it for you. You could even go as far as saying, okay, I know everything about this pipe. Tell me what kind of a surface roughness I need in the pipe. What's the friction factor? So you could just solve it from that angle. Do that. And lastly, you may know everything about your pipe. You measured everything, and you say, well, now that I know everything, tell me what are the losses in the system. And it calculates the total losses, minor losses in the system for you. So you could actually use this to see if there's any falling effect or something is stuck in the system, and gives you an idea for the restrictions in the pipe, and see if that makes sense what you're expecting. And another quick calculation that we usually do is that you can look at a heat exchanger, see if get a feel for the design of it. Here we're looking at a big condenser in a power plant, and you have figure out what are the losses through the cold plate. As I said, just looking up fluid properties, you could use that and the thermodynamic component characterization. So this brings us to the end of our presentation. ThermoFlo is a tool, as we see, that you could use it in a lot of different ways. As it shows, it's very valuable in design and evaluation of the thermal management systems. You can accurately model these things using a variety of different techniques, and it's very easy to use. It comes down to drag and dropping things on the screen. And because of it, you don't have to model worst case, and you can actually model real cases. You can actually, see what would happen, what's your efficiency and things of that nature. Anyway, so that's the end of our presentation, and I thank you for your time. And if you have any questions, Hamish and I will be happy to answer.